Okay, so this is the coding challenge. Quite a lot of text in there, isn't there? Is there a way of like condensing that?
Yeah, I guess I could quickly kind of describe it. Basically, you get a list of instructions. It's text. It's just a pure text string, and in there is a list of instructions. It's like a direction. So it's either R, L, U, or D. I guess you guess what they followed by a space and then a number. So this is how many steps you need to take in a certain direction. Essentially, this is a list of instructions to tell you where the first knot in a rope is going to move, and then there's a tail of this rope. So there's two knots in this rope, should I say? So one's the head, one's the tail. The head moves according to this list of instructions, and the tail follows based on some rules that are defined in all this text up here. That's the premise of it generally. I don't know if
that makes perfect. That makes sense to me.
Yeah.
That makes sense to me.
The general rule is the tail can't be further than one space away from the head at any point. So every move you've got to move the tail corresponding. Now, so it sounds fairly straightforward. I think out of all the challenges in code, it's one of the more straightforward ones, and it's pretty easy to kind of work out how you do it. Yeah, so this is a small example on the left hand side, which yeah, it's just a list of instructions which are given. The actual file, I think, let's have a look at that in the block diagram. I've put it here, but it's like 1600 lines long, so it's pretty, you know, you've got to get efficiency right on the code to get it to run in a reasonable amount of time, and that's generally the kind of issue you face when you're looking at the advent of code challenges. Like, you know, it looks simple from that list of instructions there, but when you get lots and lots of lines, then it becomes more difficult. But yeah, essentially, take that list and generate these motions and see what happens. So the idea in the end is to count how many squares or how many positions the head has been in as you run through all these instructions. So yeah, you just sort of, it's the head or the tail? I don't know. No, it's the tail. So you've got to count how many positions the tail. Obviously, if you did it from just the head, there's this first knot, then it's a lot simpler. But you've got to actually follow where this tail went, count how many squares it actually went in over the whole journey, and then that's the answer.
How many bits between the tail and the head?
There's just in the first part, which is what you've given us as the challenge. It's just one head, one tail.
So literally they're next to each other.
So they're next to, well, yeah, they should stay next to each other.
Theory, yeah.
But yeah, in the second part, it was something like 10.
Okay,
it's like
a shade as opposed to
I think probably I'll just run it, see what happens. I'll run it slowly. So as you can see, that's basically me following a list of instructions. I'm not using the example on the left, I'm using the full list of instructions. So it's working down through what was something like 2,000 instructions. It's really slow, so I'm going to get rid of that delay. But basically, I put that delay in so you can see it moving around on that screen. So it's basically like a little worm moving around on there. But I put a delay in to make it a little bit slower so we can see it. And I put that on as well so we can make it go really nice and fast. So basically just deferring the panel update on there. Yeah, it should eventually get down. You see it's going 500, 400, 300, 200, 100, down to 0. Yeah, and then it eventually gives us the answer. So
you're only counting the
where the tail's been.
Yeah, and if he goes there twice, it's only counted as one, or
yeah. So I mean, we can walk through that bit of code. essentially this last bit. Well, this bit internally here. So this bit is where we're counting all the positions that the tail has been to. Probably a better way of doing that using a collection or something like that. So what I'm doing is building up an array of every position that it's been to, and then concatenating that array, and then adding the first position, and then removing all the duplicates. So then just counting the number of items in that array. So that's the kind of end of it. Yeah, I think the main logic of it, I guess, the structure is building up an array of XY coordinates where the head and the tail are. So that's this side of things, initializing them to 0, and then moving them based on the instructions that we're getting from the array at the bottom there. So moving the head is fairly straightforward. So it's just a case of working out which direction it is and moving one space in that direction. And for every instruction, it might be 1 step or 2 step or 6 steps. So we just do loop through that 6 times or 5 times or whatever we need to do. Moving the tail is a bit more difficult because you've got to base it on where the head is. And there's some rules in that set of instructions about where the how far away it can be, and it could literally, I think the rules were that you can only be 1 space away, whether that's up, down, left or right, or diagonal. So, they basically created a set of rules around that, and that's the outcome here. So if it's basically worked out the Manhattan distance, which is this,
2 sides of the square.
Yeah, the size of the square stuff. Yeah, so Manhattan distance is, you can't go diagonally. You've got to go up and across. Like you're looking at the map of Manhattan. You can only go on the roads. You can't go through the buildings. So that's where that comes from. If it's 2 spaces away, then this was the hardest bit. I shouldn't have gone for that one first. But essentially, if it's two spaces away, if it's up, down, left, or right, then move the tail towards the head. If it's diagonal, then it's only one space away essentially. So then you don't need to move. So that's why I've got this 0.
That's a diagonally.
It's fine. It can be
space away diagonal. So
it's
moved like that, but you don't have to move the tail.
Correct.
Because you're already 1 space away.
Yes. So the only reason you need to move in that instance if it's up, down, left, or right, 2 spaces directly, and then if it's the other rule was if it's not directly up or down or left or right from it, if it's some way diagonal, it might not be directly diagonal, but it could be kind of 2 spaces up or 1 across, then move diagonal. So that's this case essentially. That's it. I guess that was moving the tail relative to the head, and the rest was working out how getting rid of all the duplicate entries in there and giving you the number of spaces. So,
anyone want to dig into anything specific on those? You're talking about efficiency. What do you need to do to make it quick?
I think
specific, naturally quick.
I think in this case this was pretty quick already. I guess the one or 2 things I've done in there is use in-place element structures. So because working on quite a in this case it's a small array. It's only 2 elements in there. For this one, in the other one there's 10 elements. I guess it's not too inefficient to kind of pull out one bit of the array and change it, but yeah, in-place element structures kind of improve efficiency on that one. Do some of these. Not trying to copy arrays around was the main kind of consideration, just making sure we keep doing one, keep one array all the time. I think probably if I got rid of this bit to do with updating the front panel, that would speed things up quite a lot. Even though I've got deferred panel updates in there, we're still talking to the front panel there quite a lot. So yeah, there's one or two things I'll probably improve on that. I like the second part with 10. Just so P2. So on part 2, what we had to do was expand on that a little bit more. So I had like 10. We had 10 knots, and they all had to follow each other with the same rules. So the first one moves, and then all the rest kind of follow in respect to that. So it makes a nice sort of snake as it moves through. Yeah, like that. As you can see, it kind of.
The tail hardly moved, like the last tail.
Yeah, yeah, because the front tail's moving around a lot. It's going back on itself a lot. The last part, very much, and all of a sudden, kind of rolls off somewhere. Yeah, fixed one time.
The difference between that and P1. They could just do the same thing but for every knot.
Yeah, so yeah, I suppose we can have a look at that a little bit. In the move tail section, that now, so the move head, in fact, this code's exactly the same. The code's exactly the same for both parts, yeah. The only difference is that number of knots there, so that builds up an array of 10 elements rather than 2. The move head is exactly the same, that just moves the head piece. The move tail is, yeah, it's still exactly the same bit of code. But yeah, we're pulling out each individual element. So starting at the head, we move the head, then we look at each next part of the rope in turn and pull that out, move it, and then move the next one in relation to it. So there's no difference between the two bits. Yeah.
Is that exactly the same code?
Yeah, it's the same code.
Is
yeah.
it?
Yeah, there's no difference.
You just change the size of that array to reflect.
Yeah, and I think obviously I wouldn't have done that naturally. I think I went back and kind of redid it all when I did part 2.
Yeah, that's what I mean. Yeah, you did preempt that.
So
to me, it looks like I've been running quite slowly for what it's doing. Do you know what's taking?
yeah, so the question's about it running slowly and why is it running slowly? Essentially, is that to do with the front panel? I've put a breakpoint on there now. So I think in answer to your question, yeah, there's a lot of front panel updates. Essentially, that's running every individual movement. We're updating the front panel, so there's absolutely loads of panel updates going on. You can see that block there is doing all the front panel updates. It's also changing the size of the graph, and as that graph gets bigger, the graph slows. You know, that itself slows things down. So you kind of, yeah, taking all that visualization out, it runs in the like blink of an eye. Yeah, yeah. So there's certain things I kind of started to play around with in terms of improving that. But
yeah, well, I've come across loads of times that you see you say very it's not to do something. It's just not that big, but it seems to be hiding back there.
yeah, and I mean, you've probably seen on there on the front panel. I've got this defer panel updates button. Back. I'll find it again now. But yeah, I put this defer panel updates. It's, to be honest, it's running a lot slower on Chris's laptop than it was on. Yeah, so I think, yeah, deferring panel updates so that it only happens at it's only happening ones per set of instructions. Like I've got this, you know, for each line I could have 15 instructions times however many knots there are. So I'm just jumping from one image to the next. That sort of speed things up a lot. But yeah, resizing that graph makes a big difference as well.
LAMP use UI thread is just one thread, the UI thread. So anything you have that's resizing up, do anything with property nodes.
Yeah.
You're accessing the UI thread and locking other instances of UI thread eventually.
Yeah.
Yeah.
There's, I guess, deferring panel updates, though, that stops that from happening.
Yeah, but yeah, it essentially stops that update. You're still calling to the UI thread every time you call property node. But all these property nodes are still calling into the UI thread. But yeah, you're actually stopping the panel. It's
So-
changing.
So one way to make that much better, much more efficient. Here's really slow. This is laptop. One way to make that really efficient would be to kind of bundle all that up into a queue or something like that, or a notifier, and only do it once at the end.
Yeah.
And yeah.
That's not great, cheers for saying.
Yeah.
I'll just quickly mention, because otherwise Jenny will give me a bollocking. The GDevCon, Tom mentioned it, tickets are on sale now and you get a discount for the next 25 days, something like that. And then it cuts off when it's back to full price. So get your tickets in ASAP. Also presenters, anyone looking to present, the presentation call is open. So get those in if you're keen to get a slot at GDevCon, you get a free ticket. Yeah, get involved in that as well. And if you're thinking about attending, it's in Glasgow as well. That's going to tip you over the edge, and it definitely get your fried Mars bar, all that kind of stuff. So yeah, that's my last bit. Now I'm done. I won't get told off. Thanks everybody for coming. Thanks Mike, who's left the room, but he's helped organise with Jeeves. Thanks for connecting us up as well, mate. That was really helpful. I think that's all that's left is to say thank you and see you next time. Cheers for bringing the hardware, guys. And nice to see it. Cheerio, people online. You can't see me because I'm on the side of the camera. And we'll see you again next time. See you later.